going to talk now about change of variables, mostly the polar coordinates. That is, we want to learn how to change some rectangular integrals using the rectangular coordinates, to integrals, double integrals actually, using polar coordinates to make the integral easier. So first, why don't we practice integrating in polar coordinates? It's just different letters. It's nothing but different letters, and possibly you have a better chance of seeing trig functions, sines, cosines. Okay, first integral is that one. I bring this 3 out in front, and I bring the sign in front of the first integral. I'm calling this the first integral, okay? R squared dr d theta, 0 to 6. So basically, I want to know what that is. I can do that on the side maybe. 0 to 6 r squared dr, r cubed over 3 from 0 to 6. This is 6 cubed over 3. Really minus 0 cubed, which is 0. I really don't want to figure out what 6 cubed is, so I don't really need to, because I know that 3 is going to go into one of the 6's. This is 36. 2 times 36 is 72. This mess inside the big brackets is 72, which I will bring out in front. 2 times 72, I guess, is 216. Integral of sine theta d theta. I did what was in the middle. What was in the middle was that first integral that we had to do, which is 72. Okay, and this goes from 0 to 2 pi. The integral of the integral of sine theta is negative cosine theta from 0 to 2 pi. Now, I hate negatives. So basically, I'm factoring out the 216. I hate negatives. If I just make it positive cosine theta, then I have to change the order of the limits. Okay, cosine of 0 is 1 minus the cosine of 2 pi is 1. That's 0. 216 times 0 is 0. So the very top line is just a complicated way of saying 0. Somebody asked you, and you probably didn't know it 5 minutes ago or 20 seconds ago. You probably won't know it tomorrow. But right now, somebody asked you, what is 114 times the integral from 0 to 2 pi of the integral from 0 to 6 is 3r squared sine theta dr d theta? I would hope you would say 0. In fact, even if this 3 wasn't there, you should say 0. Because this 3 comes out in front anyways. And if what's in the bracket is 0, remember, what's in the bracket is 3 times this. And if 3 times this is 0, it's not the 3 that equals 0, it's the this that equals 0. This is 0. 114 times 3 times 0 is 0. So, polar integrals are no real different. Instead of x and y's, you have r and thetas. If somebody asked you to find the area of this graph, find the area of this, using double integrals. You're told that r is equal to 6 cosine theta. This is going to be 6 out there. You want to use double integrals. Now, a couple of things, or at least one big thing. You know, normally it's dx dy or dy dx. Well, it turns out that dx dy You can prove this, of course. And polar is r dr d theta. dx dy is r dr d theta. So since we're going to do polar, it'll be r dr d theta. Remember, so I want to know, for example, this r value. I want to know the start of r and the finish of r. Well, the start of r is 0. No matter where I go, r starts at 0. And where it ends up at is another r, which is known as 6 cosine theta. 6 cosine theta. And turns out that theta is going from 0 to 2 pi. 0 to 2 pi. Of course, you can go from 0 to pi and then double the answer. And after all, cosine of 0 is 1 times 6 is 6. You get a bigger angle, a bigger angle. Bigger angle. Let me try this a bit more neatly. You have 0, you have 5 radians, pi over 2, pi over 5 radians, pi over 4, pi over 3. And then eventually right here is pi over 2. And then the other half will bring you all the way back to 2 pi. So you can integrate from 0 to 2 pi. You can go from 0 to pi and then double it, whichever you prefer. And you didn't find the equation of the circle. I mean, the center is at 0, so actually, if you want to know the area, you don't have to integrate at all. There's the center, that's 3, and that's 3. The radius is 3. I know the diameter out there is 6 because cosine of 0 is 1 and 6 times 1 is 6. So r is 6 right here. So it's going to be, the area is going to be pi times the radius squared. So if you work this out, you best get 9 pi. So working it out is nothing more than integrating with different letters. If you wanted to, if you have a circle and it's centered at the origin, and r is 8, the radius is 8. Well, boom, pi a squared better be the answer. Pi a squared better be the answer to the area. It's a double integral r dr d theta. R goes from 0 to 8. Theta goes from 0 to 2 pi. I do this integral first. That integral is r squared over 2 from 0 to 8, which is a squared over 2 minus 0. It's a squared over 2 d theta. But this has nothing to do with theta. It's a constant. I can factor it out in front. So it's that constant times the integral from 0 to 2 pi of d theta. But the integral of d theta is theta from 0 to 2 pi. This is a squared over 2 times 2 pi minus 0. This cancels out, and you get a squared pi, which is the same as pi a squared, which we said we'd get. So we just derived something that the area of our circle of radius a is pi a squared. Now you may say, but you only found the area if it's centered at the origin. Well, that area of the circle that remains on the board is fixed. It's fixed. The area is pi a squared. Well, if I move the origin up there, is this area still not pi a squared? If I put the origin right here, is this area going to change just because I move two lines that have nothing to do with the graph from one place to the next? The answer is no. So there's the area of the circle. And if you replace a with r, it's pi r squared. Now, here's an interesting one. Suppose that you want to find the area outside of this circle, but inside this circle. That is, you want to find this area. You want to find this area. And I'm telling you, the equation of the first one is r is 2, and the second one is r is 4. What's the double integral? R, dr, d theta. Well, r. Okay, so have to find r limits first. Well, that's the r. Okay, the length is the bigger r minus the smaller r. The bigger r minus the smaller r. R goes from 2 to 4. Actually, I take that back. R right here is 2. R right here is 4. R goes from 2 to 4. The angle goes all the way around. Goes from 2 to 4. Now, you can go, you don't have to go all the way around. I mean, you can go from 0 to 1 radian. Find out this area here, and then multiply it by 2 pi. Or you can find this area here. Go from 0 to pi over 4. And the answer you get, multiply it by 4. Why by 4? Because this area is the same as this piece, which is the same as this piece, which is the same as this piece. There's 4 of them. You only counted 1. Now, we should know the answer. It's going to be the answer of the whole big circle, which includes this area inside here, which is pi 4 squared. And then you take away the part you don't want. You take away pi times 2 squared, which is this area. And what you're left with is exactly what you want. And factor out pi. You get 4 squared minus 2 squared. You get pi times 12 or 12 pi. Let's work this one out. Integral from 0 to 2 pi. This integral will be r squared over 2 from 2 to 4 times d theta. 0 to 2 pi. Well, when you plug in 4, you get 16 minus when you plug over 2. And when you plug in 2, you get 4 over 2. This is 12 over 2, or 6. This is 6. 16 minus 4. Okay, you get 6. But it's a constant. I can put it out in front. D theta. Well, there's 6. The integral of d theta is just theta, from 0 to 2 pi. You plug in 2 pi for theta, minus, then you plug in 0. You get, this is 2 pi. 6 times 2 pi is 12 pi. Exactly what we were supposed to get. These are great problems to see on an exam because, especially myself who makes a lot of silly errors, I know the answer going into it. It wasn't that hard for me to do this calculation. And I did every step to it. I factored out pi. I would just go 16 minus 4 is 12 pi. That's how long it would take me to do that. I would go 16 pi minus 4 pi. 16 minus 4 is 12 pi. And then make darn sure that when I do all of this work, I get 12 pi. amazingly I did. And if your teacher does not say to use double integrals, you just write down the answer, 12 pi. Show the work how you got 12 pi. Now, we're going to talk about how we're going to look at an example where it might be easier to go from rectangular coordinates, x's and y's, to polar coordinates, thetas and r's. Okay. So what we know is that y is r sine theta, and we know that dx dy is r dr d theta. So the product of those two, which is right here, will be the product of these two, r squared sine theta dr d theta. Okay, so I just learned a big piece. R squared sine theta dr d theta. The fact that this looks like a circle, a squared minus y squared, looks like a circle. That's what leads me to think polar. Okay, so now when I look here, I see x. That is, these are x limits. X fluctuates between 0 and the square root of a squared minus y squared. In particular, x is greater than 0. And y goes between 0 and a. Y goes between 0 and a. In particular, y is positive. Just so I don't forget, if x is positive and y is positive, we are in quadrant 1. I won't draw anything outside of quadrant 1. So I'm really going to lead myself to actually draw something outside of quadrant 1. And I can't help but remembering not to. I crossed it out. Since x is positive, I can square both sides. And I get x squared is less than or equal to a squared minus y squared. Bringing the a squared to the other side, the y squared to the other side, I get x squared plus y squared is less than a squared. That's a circle of radius a. That's just a circle of radius a. Now, if I just drew the circle of radius a, I'm in all 4 quadrants. But I know that, oops, I'm not in all 4 quadrants. Let me not get carried away. I'm only in the first quadrant. Okay, I am only in the first quadrant. That, and, y does go from 0 to a. 0 to a. And I'm less than this circle, less than or equal to. That is, I'm inside the circle. Okay. Now, the radius, r always originates from the origin, from the pole. And every place on this red circle, r is a. And at the pole, r is always 0. So, and no matter which r I draw, it always goes from one r to the other. It always goes from 0 to a. So, r goes from 0 to a. And theta, let me draw this picture again, because I drew one a lot. Theta goes from 0 to a little bigger, to bigger, pi over 4, eventually pi over 2. It goes from 0 pi over 2. And that's the integral that you would need to solve. And this integral is a lot easier to solve than the one right above it. Changing to polar coordinates made this problem a lot easier. Fine, we spent a lot of time converting it. But sometimes you might not be able to do it with integration. You might have to, in rectangular, you might have to resort to approximation techniques like Simpson's method or trapezoidal method, things like that. But you go in the polar, boom, 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 you get, it works out nicely, you even get an exact answer. Here's a problem. I really think I wouldn't want to do this using using rectangular. But it's the integral nonetheless from 0 to 2, or the rectangular integral from 0 to 2, the integral from 0 to 2x minus x squared, xy dy dx. Okay. Well, x is r cosine theta, y is r sine theta, and dy dx or dx dy is r dr d theta. So when you multiply these three, you get exactly xy dy dx. And when you multiply the other three, you get r cubed. R times r is r cubed times sine theta, sine theta times cosine theta times dr d theta. So you get r cubed sine theta cosine theta dr d theta. dr, that means first I have to put down the r units. So maybe that was a bit premature to talk about the r limits. That's y. So these limits are y's. Y fluctuates between 0 and the square root of 2x minus x squared, and x fluctuates between 0 and 2. 0 and 2. So once again, x and y are positive. X is bigger than 0, and y is bigger than 0. So we are once again in quadrant 1. Okay, we have to try our best not to forget that. We are only in quadrant 1. Okay. Since y is positive, I can square both sides. And I'm going to set the right side equal to 0. That is, I'm going to bring everything on the left side over. I'm going to bring everything on the right side over to the left side. So it's x squared minus 2x plus y squared is less than or equal to 0. I'm going to complete the square. Go back and review how to complete the square. Because adding the 1 made what's inside that bracket something squared. I take half of that number and I square it. That's what I add. Half of negative 2, I want to square. Half of negative 2 is negative 1. And I square it, I get 1. That's why I added 1. What perfect square is it? It's x minus half of that number. Half of negative 2 is right there. It's x followed by half of negative 2, which is negative 1. Plus y squared is less than or equal to 1. Well, if it was equal, that's a circle. That is a circle whose center is at 1, 0. To find the center, the x value is what makes this 0, which is x is 1. 1 makes that 0. Y is 0. And that's r squared. What do you square to get 1? 1. So it's centered at 1, and the radius is 1. So it goes 1 to the left and 1 to the right, among other points. That is, it goes like that. Now that's just the surface. I'm multiplying it by xy. So it won't just be the area or half the area of a circle of radius 1. Now again, it's not the whole circle because x and y were positive. It's just the top half. It's just the top half. Because if the center has an x value of 1 and you go 1 to the right, you're ending at 2. Those points are on their polar curve, y equals, or r equals, 2 cosine theta. This r equals 2 cosine theta. So the r's, they go from 0 to 2 cosine theta. The r's, they start at 0, they finish at 2 cosine theta. Okay. 0 to 2 cosine theta. Remember, that's r, so those are r limits. What does theta go from? Well, here theta is 0, a little bit more than 0, a little bit more, pi over 4, pi over 3, eventually pi over 2. Brings you right back here. The cosine of pi over 2 is 0. A little bit less than pi over 2, you'd be right there. But it goes to pi over 2, from 0 to pi over 2. And there's your conversion. There is your conversion. Okay, convert from rectangular to polar coordinates. Convert a double integral in rectangular coordinates to polar coordinates. Okay. Now, suppose you wanted to convert this to polar coordinates. Let's write it down, of course, first. Let's figure out what those pieces will be. You know that x's are r cosine theta, y is r sine theta, and dy dx, which is the same as dx dy, this is r dr d theta. You multiply the less, you get what I have boxed in both intervals. You multiply the right, so you get r cubed sine theta times cosine theta times dr d theta. Okay. So that is what xy dy dx is. And it's the same in both intervals. We're adding two double integrals, and the integrands are the same. Let's look at what we're integrating over. Let's look at it very carefully. The first integral is with respect to y. Y goes between 0 and x. Okay? Alright. Won't argue that. And x goes between those two numbers. 0 and 5 square root of 2 over 2. Let's graph this. Let's graph. So we know x and y are positive. So we're in quadrant 1. Y is equal to x goes this way. So y is less than x. It's everything below the line. So y is positive. Y is positive. That's why I didn't go down below the x-axis. And we know that x goes between 0 and 5 square root of 2 over 2. In fact, now I should draw this line. That is our region that we're integrating over. This is the region for the first integral. The first double integral. Now we're adding on some more area. Well, let's find the surface. First is dy. So these are y intervals. Y goes between 0 and the square root of 25 minus x squared. Okay? And x goes between these numbers. X goes between 5 square root of 2 over 2 and 5. And since 5 square root of 2 over 2 is positive, x is bigger than a positive number, and y is greater than or equal to 0. That is, x and y are both positive. Now, since y is positive, I can square both sides, and the inequality doesn't change. And for example, negative 15 is less than 10. But if I square both sides, and I leave the symbol the same, I'm wrong. 225 is not less than 100. But if things are both positive, you can get away with it. Will it always change if one is positive and one is negative? Negative 2 is less than 10, but when I square both sides, it's still true. So when things are, when they're less than 0, you can't do it. Not if you don't know the values. Like, I don't know what y is. I don't know what x is. But nonetheless, since they're positive, I can do this. Bring the x squared to the other side. You get x squared plus y squared equals 25. Now, remember that this line over here was y equal x. I know the x value is 5 square root of 2 over 2, so the y value must be the same. And if you notice something, if I square the x value, I get 5 squared times square root of 2 squared over 2 squared. I get 25 over 2. And if I add on what happens when I square the y value, I'm going to get the same answer. It's the same value. 25 over 2 plus 25 over 2 is 25. It's that number. This is the circle of radius 5, centered at the origin. It is the circle of radius 5. It is only in quadrant 1. And, not going to believe this, look at how this comes together. X, amazingly, is between 5 square root of 2 over 2 and 5. That is x, here is 5. X is only in between here. That is, this piece is gone. This here is the region from the second integral. But that's just a piece of a circle. Combining these, okay, let's just erase a lot. Combining everything, we just have the sector of the circle. I mean, what we have right now is just, let me do this. What we have is this. Okay, so I'm going to go to polar. Now remember, we've already said that not only were these both the same, but, see if I remember it. It was r cubed sine theta cosine theta dr d theta. Now, this is neat, how it all came together. This is r. And so, in polar coordinates, this circle, or a portion of the circle, is r is 5. No matter which I draw, the first r is 0, and the second r is 5. It goes from 0 to 5. It always goes from 0 to 5. Okay, 0 to 5. And theta, well, remember, the x's and y's were both the same. It was 5 square root of 2 over 2, 5 square root of 2 over 2. So if I want to find this angle, if I want to know this angle, well, I know it starts at 0. I want to know the big one. The angle starts at 0. And I know a lot about this. I know that the x value is 5 square root of 2 over 2, and the y value is 5 square root of 2 over 2. So the tangent of the angle is y over x. I don't care how unfriendly those numbers look. You divide the same numbers, you get 1. When the tangent is 1, the angle is pi over 4. Or you can say, if the x's and y's at this point are the same, that angle is pi over 4. However you get it, the angle goes from 0 to pi over 4. And I just converted from rectangular, a sum of 2 double rectangular integrals, into one polar. I put the pieces together. They fit like a glove. They really did fit like a glove. That's because I understood what the regions look like. And they fit together into one whole region. Now, suppose you're asked to use polar coordinates to evaluate the double integral over some region of f of xy dx. And in this problem, you're told that f of xy is just add the x's and the y's. And the region is the set of all points bounded by x squared plus y squared is less than or equal to 4, and x and y are non-negative. Well, x squared plus y squared equals the 4 is this, where the radius is 2. Remember, that's r squared, so r is 2. And since it says less than, we're talking about the points inside. Talking about the points inside, and it didn't only say less than, it also said equal. That allows us to include the points on the circle. But x and y have to be positive. But x and y are positive. That means we're only in quadrant 1. We have to get rid of a lot of this stuff. We are only in quadrant 1. Okay, I guess so we need to get rid of the whole picture. So we're in quadrant 1, and we are a portion of a circle of radius 2. We're like this. 2, 2. Okay, so polar. Now, this becomes r cosine theta plus r sine theta. But I can factor out the r. dA is r dr d theta. So r times the r in front will make it r squared. And r goes from, well, this is r equals 2. And right at that pole, r is 0. So r always goes from 0 to 2, 0 to 2, 0 to 2. R goes from 0 to 2. And theta goes from, starts at 0, a little bit bigger, pi over 3, pi over 4, well, pi over 4, then pi over 3, and eventually pi over 2. Goes from 0 to pi over 2. And this is the integral that you would solve. And the r that I'm erasing got multiplied by the r in front. And you can integrate this. Why don't we do this one? 0 to pi over 2. This, having nothing to do with r's, can come in front of that integral sign. And you get r cubed over 3. This is r cubed over 3 from 0 to 2. 8/3 times the constant, which is right there in front. D theta. Well, the 8/3, that can come in front now, all the way in front. So we have 8/3 times this integral. But the integral of cosine theta is sine theta, plus the integral of sine theta d theta is negative cosine theta. And this goes from 0 to pi over 2. And once we do that substitution, we will have our answer. Eight-thirds. The sine of pi over 2 is 1. So the cosine must be 0. When sine or cosine is plus or minus 1, the other one is 0. That is, if sine theta is plus or minus 1 at some angle, cosine theta will be 0. Okay, minus. The sine of 0 is 0. Minus. That means the cosine of 0 will be plus or minus 1, and it's 1. So what we have is 8/3 times 1 minus negative 1. Now you all know that 1 minus 1 is 0. So clearly this will not be 0. Because that might be 1 and that might be minus, but that surely isn't 1. I've never seen a student write down 1 and it looks like that. They always wrote 1 down that way. Some people may write it down that way. 1 minus negative 1 is 2. So 8 times 2 is 16 over 3. The answer is 16 over 3. Going from rectangular to polar coordinates, well, for one thing, it's fun. You have to look at the region and see what x's go between and what y goes between. Don't let it be brutal. It's not meant to be brutal. It's meant to be beautiful. They both start with B's, but beautiful was nicer. Let's set up one more. Suppose you had that f of xy was 9 minus x squared minus y squared. And the region was x squared plus y squared is less than or equal to 9, and x and y are both positive. X is non-negative and y is non-negative. Remember, 0 is not positive, so I don't want to say x and y are positive. They can be 0. Okay, well, this is x squared plus y squared equals 9 in quadrant 1. Because x and y are positive means quadrant 1. That's a circle of radius 3. Remember, that would be r squared. So r would be 3. And it's less than. Because everything on that circle and inside. But in quadrant 1. Okay, so basically, so now this is going to become, this is 9 minus x squared plus y squared. But x squared plus y squared is r squared. So, we're integrating, remember, we're integrating f of x, y over some area with respect to our region. Okay. F of x, y in polar is just 9 minus r squared. This is that. dA is r, dr, d theta. And now the region. Well, first, we have to put r's here. And r goes from here, r is 0. And everywhere on that arc, r is 3. R goes from 0 to 3, 0 to 3, 0 to 3, 0 to 3, 0 to 3. And the angle is just a quarter of the circle. Goes from 0 to pi over 2. And there it is. I would distribute the r, and then integration would be easy. This mess would just be 9r minus r cubed. So this will become the integral from 0 to pi over 2 d theta, and what's inside would be, this integral is 9r squared over 2 minus r to the 4 over 4 from 0 to 3. Work that out. It's going to be a constant. Call it k because I don't want to figure it out. This mess is some constant. Pull it out in front. From 0 to pi over 2 d theta. The integral of d theta is theta. From 0 to pi over 2. That will give you that constant times pi over 2. Go and just figure out what that constant is. It's 9 times 3 squared over 2 minus 3 to the 4th over 4. And when you plug in 0, you get 0. That is what I call k. And there it is. It's a lot easier than using rectangular. Finding the limits were very smooth and easy. Okay, finding the limits for the other case is not going to be so easy. Remember, when you have integrals that involve a squared minus x squared, you end up with trig inverse functions as their integrals. You don't want to deal with that. I'd rather deal with r equals 3 as a limit than the square root of a squared minus or x squared. So suppose you want to find the volume bounded by z equals xy, x squared plus y squared equals 1, and the first octant. That means x, y, and z are positive. But basically, what happens is you have x and y, and z's coming out the board. Everything on the board and outward over here is the first octant. Everything in what's normally quadrant 2, but out of the board, is the second octant, and then the third octant, and the fourth octant. That's out of the board. But now, you come back, and you have the fixed octant. It's into the board. You have above the board and below the board. Here. In front of the board and behind the board. You have 4 of these regions. So the first octant, that's where x, y, and z are positive. In the second octant, x is negative, y is positive, z is positive. Third one, x is, of course, negative, y is negative, and z is positive. Fourth one, x is positive, y is negative, and z is positive. For the 5th, 6th, 7th, and 8th octant, these four will be the same, except they all have this one change. It becomes less than. Z is negative. Z is negative. So all we know is x, y, and z are positive. X, y, and z are positive. Okay. So whenever I see x squared plus y squared, I think polar. This tells me that, what does it tell me? It tells me that r is 1, because this is r. And this tells me x, y, and z are all positive, or 0. Polar. X is r cosine theta, or y is r sine theta. You multiply, you get r squared sine theta cosine theta. Now, if you were to graph this, we're in the first octant. R always goes from 0 to 1. And R is 1. R goes from 0 to 1. So we have the double integral of the function, which is z, times r dr d theta. So this will become r to the third. And r goes from 0 to 1. And the angle goes from 0 to pi over 2. That one is done. Okay, let's do one more. Can use a double integral and polar coordinates to find the volume of the solid bounded by the graphs of these equations. Z is equal to the square root of x squared plus y squared. Z is equal to 0. Z is equal to 0. And x squared plus y squared is bigger than 4. And also x squared plus y squared is less than, it's a good number, less than 16. Alright. Now, this is never negative, so I really think that it can be 0. So I think saying, okay, z equals 0, that's the xy plane. Now, and z is always positive or equal to 0. So you're bounded by the xy plane and this mess on top. And if you square both sides, you get that z squared is x squared plus y squared, but z is positive. So when, here's the z. When z is 0, you get x squared plus y squared is 0. When z is 1, you get x squared plus y squared is 1, which looks like that. When z is 2, you get x squared plus y squared equals 4. It's a circular radius 2. And when z is 3, you get x squared plus y squared is 9. Basically, you're getting this shape. That's what that is. Okay. Now, in the xy plane, we have x squared plus y squared is, say, equal to 4. That's the circle of radius 2. But we want to be bigger than 4 or equal to it. That's on the circle. Those are the points on the circle and outside the circle. But x squared plus y squared is 16 is a bigger circle, and it has to be on the circle or inside. Less than means inside. It is your hair. Now, imagine we took something that looked like this. A donut. I probably drew it a little bit too big compared to my z equation, but basically, we take a donut like this, and we put it right there, and we push down, and we want to see what part of this gets replaced. When we move this down, basically it's cutting out this piece. That is, if you were looking right down here, you would see that cutout. You would see this missing. You would keep seeing that missing. You'd be, oh my, well, what happened to that? It's not there anymore. Okay, you take this and you push it straight down, and it removes everything that's right in its place, in its space. Doesn't move anything else. And the question is, what is that volume? What is that volume? That is what we want to know. What is that volume? Well, give me a moment or two and we will figure it out. So, a couple of comments. This is really r. The square root of x squared plus y squared is r. What we want to do is do the double integral over our region of z dx dy. But let's convert to polar. Z is r. Z is r. Dx dy is r, so it becomes r squared, dr d theta. Now, with respect to r, let's look at the bottom left picture. Here, r is 2 and 4. So, r goes from here to here. Always. Goes from here to here. Goes from 2 to 4. Okay, 2 to 4. That was quick. Theta goes from 0 to 2 pi. Because it goes all the way around. And it's going to cut that out. And integrating this is a snap, so we'll do it. R cubed over 3. This integral is r cubed over 3 from 2 to 4. 4 cubed is 64 over 3 minus 8 over 3, which is 56 over 3. So it's the integral from 0 to 2 pi of 56 over 3, which is a constant. I'll pull it out in front. This mess was just 56 over 3 d theta. So you get 56 over 3 theta from 0 to 2 pi. But that's just 2 pi. 56 times 2 pi is 112 pi over 3. Okay. That completes this section. Good luck with it.